So this is Taylor and Mclaren series, if I'm saying that right. And let me bring up the book, see if there's anything worthwhile to mention in there. Okay. Section 9.9, you derive power series for several functions using geometric series with term-by-term differentiation and integration. In this section, you will study a general procedure for deriving a power series for a function that has the derivatives of all orders. The next theorem gives the form that every convergent power series must take. Okay, if f is represented by a power series, f of x equal to the sum of a sub n times x minus c to the n power for all x in an open interval I contains c, then a sub n is equal to f to the nth, not the nth power, the derivative. So that's the nth derivative of f of c over n factorial, and f of x equal f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared, on and on to the nth derivative of f of c over n factorial times x minus c to the n power, on forever. I think these problems are kind of challenging. I'm going to do an easy one at first. I could pick all the easy ones to show in class. But we're going to go over and use Calc Chat, because I don't see these patterns. And I struggled with that this afternoon looking for it, and I cannot see them. I can see the simple ones, but I can't see the more complex ones. Okay. And here's definition of Taylor and Maclaurin series. If function f has derivatives of all orders at x equals c, then this series is called a Taylor series for f at c. Moreover, if c is equal to 0, then the series is a Maclaurin series for f. Okay, let's take a look at this one. That f of x e to the 2x, c is equal to 0. And instructions say use the definition of a Taylor series to find the Taylor series, center of c for the function. Well, here's our definition. It's pretty straightforward to begin with. Looks like if we focus on the right-hand side, we need f prime, f double prime, all the way up. You're really trying to see a pattern. Okay, so this is the chain rule. Derivative of e to the power is e to the power times derivative of the power. So that'd be 2e to the 2x. For our second derivative, again, the derivative of e to the power is e to the power times the derivative of the power, so I have another 2 out in front. So I got 2 times 2, or 2 squared, e to the 2x. Third derivative, again, same idea. It becomes 2 to the third, e to the 2x. So what's a pattern appear to be? Yeah, so 2 to the n power, right? E to the 2x. Now that's this part right up here, except for we need to plug in the C. And you could plug it in here if you wanted to, but if I plug in 0, then I'm going to have 2 to the n, e2 times 0. 2 times 0 is 0. E to the 0 is 1, and that gives us 2 to the n. So at that point, we really have everything we need for this formula. So n equals 0 to infinity. The nth derivative of c is this right here. So it's 2 to the n over n factorial x minus c, which was 0 for this problem, the nth power. So that's 2 to the n power. X minus 0 is x. X to the n power is x to the n over n factorial, which gives us n equals 0 to infinity. This will be 2x to the n power over n factorial. Very easy problem. You look at it, it's like, oh, geez, this is nothing. But then we'll see it change dramatically on the next one. Yeah, because the key is recognizing the pattern, right? And if they're just like, there's this next one, the next one, I could no more guess that pattern. I could probably spend 2 years trying to figure out the pattern and still not get it. But some people may see those. Okay, so let's take a look at the next one. And that's actually what we'll focus on a lot on this section is we'll just look, see if we can see patterns. Plugging it in is just kind of brute force algebra type and calculus. Okay, number 7. F of x is equal to cosine x. C is equal to pi over 4. Same instructions. Again, we got to focus on the right-hand side and try to see if we can see a pattern. Right-hand side, we have f prime, f double prime, up to the nth derivative. So, derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Then ignoring the negative, the derivative of cosine is negative sine, so negative negative gives me a positive sign. And derivative of sine is cosine. Now, can I say anything about the nth derivative? Not really. I mean, it's probably going to be sine or negative sine or cosine or negative cosine. That's about all I could say. So, I can't just directly plug it in the formula like this. Okay. Well, regardless, this c here implies we need to plug c in to all of our function and derivatives. So we're going to have f of pi over 4 equals cosine of pi over 4, which is square root of 2 over 2. For our first derivative, we're going to have negative sine pi over 4, which is negative square root of 2 over 2. For our second derivative, we're going to have negative cosine pi over 4, which is negative square root of 2 over 2. For our third derivative, we're going to have sine pi over 4 is square root of 2 over 2. And for the fourth derivative, we'll have cosine pi over 4, which is square root of 2 over 2. Now this says we want to plug it into this. So I got f of c plus f prime of c times x minus c. But nice if it showed another pattern on this, but they didn't. You really have to kind of look at this to see the pattern. We have the nth derivative and n factorial down here. So for our second one, we have the second derivative up there that matches our n, so we need to have the n factorial down below. So that'll be 2 factorial times x minus c, and notice the power on the here is n, and matches the n here and n here. Plus f third derivative over 3 factorial x minus c to the third. And I'll throw one more on there since I did take it to the fourth. For 4 factorial times x minus c to the fourth. Okay, so now we're ready to plug everything in. The f of c, f prime of c, all those is these right here. So square root of 2 over 2. The f prime is negative square root of 2 over 2. X minus c, c was pi over 4. F double prime is negative, so that's negative square root of 2 over 2. And we're going to have x minus pi over 4 squared over 2 factorial. The next two are, wait a minute, next two are positive. And square root of 2 over 2, x minus pi over 4, fourth power, 4 factorial. Now, if I plugged in some missing items here, this going backwards, 4 factorial, well, there's a plus dot, dot, dot. 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. So this would be, and I could take the square root of 2 over 2 and put a clear out in front, couldn't I? Because they all had that. So this would be, what did I say, 0 factorial. Now up on top, they're all x minus pi over 4. The only thing that changes is the power. 4, 3, 2, 1, 0. And I can see the obvious patterns like that. That's not really the issue. Okay, so that's this one. Then minus, square root of 2 over 2 is gone. We're going to have x minus pi over 4 to the first power over 1 factorial minus x minus pi over 4 squared over 2 factorial plus x minus pi over 4 to the third power, 3 factorial, plus x minus pi over 4 to the fourth power over 4 factorial, dot, dot, dot. Now the square root of 2 over 2, since it's just a constant, I could put out in front, so no problem there. Obviously, this is starting at 0 and going on up, right? So if this is, what is the I? Oh, yeah. 0 to infinity. That would obviously be n factorial there. Up on top, well, that's easy. They're all x minus pi over 4. Doesn't get any simpler than that. And the power matches in, so we're still good. But look at the pattern of the signs. This is a positive 1, negative 1, negative 1, positive 1, positive 1. And I'm assuming that this would be negative, negative, positive, positive, and continue that way forever. How in the world do you build that? Now, I'm pretty sure it's negative 1 to a power. This is negative 1 to a power, so it flips back and forth. They're going to get 1. If you make it 1 to the third, you're going to get positive. We're doing positive, negative, negative, positive. There is a pattern. If you take it to the n times n plus 1 over 2, that'll give you that pattern. It's like, I wouldn't know where I've ever saw that. Then. But it's, let's see, negative 1 to the n times n plus 1 over 2. And that would be our answer. Now, if I plugged in 0, 0 here times 0 plus 1, that's 0, 0 over 2 is 0, negative 1 to the 0, so positive 1. So that matches. If I plug in n equals 1, 1 plus 1 is 2, times 1 is 2, 2 divided by 2 is 1, negative 1 to the first power is negative 1. If I plug in n equals 2, put 2 here, the 2's cancel, 2 plus 1 is 3, negative 1 to the third power is negative. 0, 1, 2. If I plug in 3, 3 plus 1 is 4, divided by 2 is 2, times 3 is 6. That gives me a positive. And you'll find as you go through, it actually does work out. Interesting enough, this is a quadratic. If I were to rewrite it, that's n squared plus n over 2, which is 1/2 n squared plus 1/2 n. Assuming I was smart enough to look at it and see that it follows a quadratic form, which I'm still wrapping my mind around that, how I plus, minus, minus, plus, plus, all ones is quadratic. But you could did this number, this form here, maybe throw a plus c in there, but then you'd need 3 of them, which would be okay. And then you do your n equals 0, n equals 1, n equals 2. And for those, I don't know why I got a 0 there, but that would be that. So then I'd have an squared plus bn plus c equals something. And then I'd have a times 0 squared plus b times 0 plus c equals, and the first one would be 1. See, that implies c is equal to 1. What if I don't start with n equals 0? What would that give it to us? So a n squared plus bn plus c equals 0. So n is 1. So 1 squared is 1. B times 1 is b plus c equals, and this should give us a negative 1. I don't think this is going to go anywhere. If I did this one, if I plug 2 in, 2 squared is 4, so that gives me 4a plus 2b plus c equals another negative 1. If I plug 3 in, I'm not sure why I'm putting 0 there. Okay, if I plug 3 in, 3 squared is 9, so I got 9a plus 3b plus c equals negative, negative. Next one's positive. So the question would become, is if I plugged out my calculator, 9, 3, 1, 1, 4, 2, 1, negative 1. Let's see if that gives us 1 half and 1 half and 0. That still goes based upon the assumption that I saw that it's quadratic, which is a big assumption. So that assumption only exists because I saw the answer. Matrix, rows by columns, 3 by 4. One negative 3, 1. Nah, I have no clue how you could look at that and just see that. But anyway, I digress. So in case you're wondering, there won't be any like this on the test. Now there might be some later on because they go from ridiculously hard, where if you have to be a genius to see the pattern, to the point where it's just, so this is super easy. It is. You just look at the table and see which one it matches. So it's just like, oh, this is easy.
So something like the first problem we did.
Even easier than that.
I think it'd be easier than that.
Well, you might be surprised.
That's pretty darn simple.
See, because you might say, well, that's easy, but doesn't cosine look pretty easy? Taking derivative of cosine flips back and forth between sine and cosine. It's like, well, that's even easier in the chain rule applied to e to a power, except for it doesn't go to a pattern. Okay, let's take a look at this one. And that's x to negative 1. So from our formula, we take derivative over and over. take a power, put it on front, lower it by 1, so this would be negative 1 over, wait a minute, let me write it out. Okay, that'd be negative x to the negative 2 or negative 1 over x squared. For our next derivative, take your power, put it on front. So negative 2 times negative 1 gives me a positive 2x, lower your power by 1, so that gives you 2 over x to the third. Take your power, put it out in front, gives us negative 6, x to the negative 4, which is negative 6 over x to the fourth. Fourth derivative gives us 24x to the negative 5. 24 over x to the fifth. I can't read my own writing. It's a negative 5, gives me something. 0 to negative 120. X to negative 6 over negative 120 over x to 6. And a pattern has developed. Well, let's plug it in. Do you see a pattern? So if you see the pattern, you don't have to actually write it out. Because if we know this, and we plug the C in, then we'll have the top part, won't we? Okay. I'll do the hard part. Now, what else? So this is x to the n. Well, this is like the 2 here, wouldn't it? So n is equal to 2. And this is a what? A 3. N plus 1. Now, you have to understand a little bit about factorials to see this pattern. 6 is 1 times 2 times 3. This is 3 factorial. 1 times 2 is 2, which is 2 factorial. And this is 1 factorial. 1 times 2 times 3 times 4 would give me 24. That's my 4 factorial. And this one comes out to 5 factorial. Now, going back to this one example I looked at, this is a 2 here. And we said that that's going to give us 2 factorial. So what's on top? N, exactly. Now, the one thing that's missing on this is about the alternating negative value. You're right, because if this was negative 1 to the first power, that'd be negative 1. If this is negative 1 to the second power, it'd be a positive. Negative 1 to the third power, so that would work, wouldn't it? Now, as you derive in that, there's no reason why you couldn't have like 2 variations of it even. Now, the question is if it works back here, because this would be like n is equal to 1, this would be n is equal to 2, n is equal to 3. If I plugged in n equals 1 here, negative 1 to the first power is negative. 1 factorial is 1. Put a 1 here, that gives me my x squared. Now, this first one here, if I plugged in n equals 0, negative 1 to 0 power, anything to 0 power is 1. 0 factorial is 1. And 0 plus 1 is 1. X to the first is x. So it works, doesn't it? In particular, though, what we're interested in is c is equal to 1. So our formula over here says this is the nth derivative of f at c. we'll plug in the 1. Not for n, but for x. And when I plug that in down here, I have 1 to the n plus 1 power, and 1 to any power is 1, so it drops away. So we're left with that right there. Okay, so now we're ready to write down our answer, because this is our formula. N equals 0 to infinity. This we just found, which would be negative 1 to the nth power n factorial over, and it tells us to automatically put n factorial there. That's interesting. Because n factorial is going to cancel right there. X minus c, c is 1, raised to the n power. So we got negative 1 to the n, x minus 1 to the n. Since these are both to the n power, I could probably put them together. So put the negative 1 times x minus 1 inside to the n power. So n equals 0 to infinity, 1 minus x to the n power. Questions on it? We'll look to see if there's any where we can derive the pattern. That was number 9. Let's look at number 11. I'm not going to actually work it. I just want to see the pattern. Okay, so after you plug that in, 0, 1, negative 1, 2, negative 6, 24. 24 and 6 and 2 and 1 are factorials. This is 1 times 2 times 3. That's 3 factorial. This is 4 factorial. 2 factorial, 1 factorial. I don't know what happens here. First two are positive. Then it's negative, positive, negative, positive.
What if it's n factorial, but it's
Negative 1 to the n.
back and forth at the end.
Negative 1 to the first power here would give you a negative. So that wouldn't work. Like I say, I'm not lying when I say I'm not good at seeing patterns. I can do the simple ones. Okay, so if we plug it in though, all of a sudden you see some things cancel away. Maybe this is one that, yeah, 5 factorial is 120. So after you do your simplification, this one I could actually work. I see this pattern. Because this would start at n equals 1. If I start at n equals 0, this is like over 1, 2, 3, 4, 5. So it's a pretty obvious pattern, right? The bottom part would be n plus 1. This would be x minus, x minus 1. They're all x minus 1s. And then this matches that power, so it'd be n plus 1. So that's where you get that. Now, how in the world do you get this? Okay, when you simplify, the 0 drops away, and then the sign alternates. That one's not too bad. Okay, so we don't see the pure seeing pattern here. We plug it in. It alternates the zeros. Let's try that. Let's try to see if we can see that, just for fun. I'm pretty sure I won't be able to see it, but they don't appear to give any kind of clue on how they come up with the pattern. Okay, so f of c plus f prime of c, x minus c plus f double prime of c, x minus c squared over 2 factorial plus dot 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 f to the nth derivative of f c, x minus c to the n over n factorial. And so that's 0. F prime is 3. X minus whatever c was, c is 0. F double prime is 0. Yeah. And then next one was negative 27. That's the first power. That's second. This would be the third. Zero plus 3x plus 0 minus 27x to the third. It's probably not a bad assumption that this is x to the n power. This is 27 is 3 to the third, isn't it? And 3 is 3 to the first. So these would be 3 to the n power. And what would that drop? Didn't put factorials in there, did I? Go and see now. Okay, so this is 1 factorial. That's 2 factorial, and this is 3 factorial. So that would imply this is over n factorial. This is a positive. It's a negative. Question becomes if I could ignore the zeros altogether. Zeros, I don't know how you could get it. So if we ignore the zeros altogether, we'd have 3x over 1 factorial minus 27 x to the third over 3 factorial. The assumption would be that we'd have 5 factorial, and I probably need another one to see a pattern. So that's 0. If I plug in fifth derivative, 243 cosine. So 243 cosine 3x. And I'm plugging in x equals 0, or yeah, 0. Cosine of 0 is 1, 243. X to the fifth. Okay, so if I said that was 0, that was 1, that was 2, the signs would be easy, wouldn't it? So that would be handled. The x to the power would be fairly easy. The bottom part, since that's 1 factorial, this is 0. Maybe I'm lying. What times n plus something else is going to give you 1. So if I plug in 0 here, that means b is equal to 1.
When you multiply 27 by 3 twice, you get to
243?
243.
Uh-huh.
It kind of seems like maybe times 3.
These are all odd, aren't they? What am I doing? Odd is either 2n minus 1 or 2n plus 1, maybe. If we plug 0 in, 1, okay. That would work on the bottom then, wouldn't it? Because if I plug 0 in, 2 times 0 is 0, plus 1 is 1 factorial. If I plug 1 in, 2 times 1 is 2, plus 1 is 3 factorial. If I plug in n equals 2, 2 times 2 is 4, plus 1 is 5 factorial. X to the, that's easy. That would be x to the 2n plus 1, right? Negative 1 would be easy. Again, 0 would be a positive. If I put 1 in there, it'd be a negative. If I put 2 in there, it'd be positive. Okay, so that'd work. The only thing that's messing me up now is this, this, and this. Three to the, like that?
No, like 3 to the 2n. The 2n is plus 1. Yeah.
Yeah, that appears to work. Let's see what I got. That's interesting. Oh, they just merged the 3 and x together. Okay, never mind. Since they're these are both the 2n plus 1, you can put the 3x together. So, okay. I have trouble with patterns. As a consequence, if I can't work it out, I'm not going to put it on a test. That type. Okay, probably not the fun of those. Let's just see. Maybe one more. They are kind of fun. It's kind of a challenge. This is what you get after you plug everything in and simplify it. 4 factorial. 0, 1, 2. If I followed a pattern, that must be x to the 0 power over, I guess, 1 factorial. Them simplifying it too much kind of messes it up. 5. Where did that 5 come from? Sure enough. That would be, the bottom part would be 2 to the n, wouldn't it? 2 to the, yeah.
Probably should go more actually.
Yeah, that's true. There really is nothing. Like, what in the world is 5? Without another one, I'm not sure if I could see the pattern. Yeah.
Also, you can't really tell for the bottom because it's not an 8.
Oh, that's right, because that'd be 6, wouldn't it? Ah. I don't want to take Drew to that again. Let's just look and see what they say. They don't even say. That's nice. Maybe there is no pattern. Maybe that's why they didn't finish the problem, or maybe they couldn't figure it out. One of the two. Interesting. Or maybe this is one where they'd say just write down 3 terms because there is no pattern. So I think there are some there. Yeah, first 3 non-zero terms. Because just because you can do this doesn't mean you can actually see a pattern or there is a pattern. No, there's no guarantee of that, I guess. Okay, nothing fun of that. Okay, now here is the binomial series, and book assumes you remember that. You remember that from algebra? I don't teach in college algebra, so I had to copy that from the book here. So this makes it pretty easy to work with. We're going to use that form to rewrite some of these. Yeah, and I don't think they. Right. And I think they wrote this down wrong. Not that I'm smart enough to actually write a calculus book, but they shouldn't have put X here. They should have put like U or something. So let me rewrite that with U. Because it gets confusing with X. So 1 plus U, and I think the K is okay, maybe, equals 1. Then my U's don't look very good. Let me put P there instead. 1 plus P to the K is equal to 1 plus KP plus K times K minus 1 p squared over 2 factorial plus k minus 1, k minus 2, p to the third over 3 factorial. Dot, 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 keeps going. Okay, now our problem we're going to look at is this one right here. It says use the binomial series to find the Maclaurin series for the function. So this is 21. F of x is equal to 1 over square root of 1 minus x. That's 1 over 1 minus x to the 1/2 power. Take that up on top and it becomes 1 minus x to the negative 1/2. Now the reason why x is a poor choice that they had in here, because we want to identify. P is whatever follows the 1, sign included. So what's P going to equal to? Negative x. And then K is going to equal to negative 1/2. Problem when you have an x here is you're saying x is equal to negative x. And it just gets convoluted. So having an additional variable in there helps out. Now we're just going to plug it in the right side. So we're going to have 1 plus k, so minus 1/2 times p, plus k, which is negative 1/2, 1/2 minus 1, p, which is negative x squared, over 2 factorial, plus, the signs really not alternate. Did I write that down right? Nope, they don't alternate. Okay. Negative 1/2, negative 1/2 minus 1, negative 1/2 minus 2, p, which we said was negative x, to the third power, over 3 factorial, plus dot, dot, dot. Negative times negative is positive, plus negative 1/2 times negative 1/2 minus 1 is negative 3/2. Negative x to the second power is x squared. 2 factorial is 2 factorial. Negative 1/2, negative 3/2, negative 5/2. And this would give me a negative x to the third over 3 factorial, dot, dot, dot. Um, 3 factorial, 2 factorial, 1 factorial, 0 factorial. Okay. X to the third, x squared, x to the first, x to the 0. Okay, that's a positive. That's going to mess me up. Oh, they're all positive. Never mind. This would be 2 to the first power, 1 up on top, and x to the first. Negative times negative is positive. 1 times 3 is 3, x squared. And then the 2 times 2 I'll put down below as 2 squared, 2 factorial. Negative x negative times negative times negative times negative is positive. 1 times 3 times 5 is 15. And I'm wondering if it'd be better if I left those as 1 times 3 times 5. But the 2 times 2 times 2 is 2 to the third, so I'll put that down here. X to the third. Now, if this is 3 factorial, that's 2 factorial, 1 factorial, and 0 factorial. 2 to the third, 2 squared, 2 to the first, 2 to the 0. But now these numbers got me messed up. If this was n equals 0, this was n equals 1, n equals 2, n equals 3, I might be able to do some of it, but not all of it. N factorial on the bottom, that's the handle those. 2 to the n power, that would handle my 2 to the powers. The x, 3, 2, 1, 0, so that'd be x to the n. Signs are all positive, so that's good. So I'm looking for, I don't know about right here. I'll come back to that one. I need a 3 here and a 15 here. So I'm thinking some number times n plus some other number is going to give me 3. And this is when n is equal to 2. When n is equal to 3, same number times n plus the same number, b, is going to give me 15. If I plug 2 in there, that gives me 2a plus b is equal to 3. If I plug 3 in there, I get 3a plus b is equal to 15. And so I got 3a plus b is equal to 15. Multiply this by -1. And I get negative 2a minus b equals negative 3. That gives me a equals 12. Well, that doesn't seem right. So a is 12. Plug that into here. I got 2 times 12 plus b is equal to 3. That'd be 3 minus 24. B is equal to negative 21. So I theorize 12n minus 21. If I plug 2 in there, 12 times 2 is 24 minus 21 is 3, which is that. If I plug 3 in, 12 times 3 is 36 minus 21 is 15. So that works, but let's see this one. N equals 1, fails. 12 times 1 is 12 minus 21 doesn't give us that. Okay, that's as good as I'm going to get. Which one was that? Number 21. Assuming they even put it in that form. They might have stopped, no, they did. Oh, they just wrote out the pattern. 2 to the n, n factorial, 2 to the n, n factorial, x to the n. And then, instead of trying to see a pattern of 1 times 3, did I screw up that one? 15. Negative 1/2 minus 2, that's negative 5/2. I didn't screw that up. They screwed it up. 3 times 5 gives you 15, not 5. Oh, they're taken to the nth. So they didn't actually multiply it together. They're just assuming 1 times 3 times 5 times 7 times 9 at the nth. Okay, I see the pattern now. Well, see, like if they did the next one, it'd be 1/2 times 3/2 times 5/2 times 7/2. And so that's why this increases by 2 each time. That seems like cheating. Yeah. I got close. That's bad. Here's the talks about the Convergence Taylor series, but not really anything to worry about there. Here's the guidelines I give you. Using the sequence developed in the first step to form Taylor coefficients and determine the interval of convergence for resulting power series. The key part is the number 1 there. There it is. Try to recognize a pattern in these numbers. Because that's the hardest part. Yeah, the rest of it is just plug it in and so forth. But seeing that pattern, that should be like in bold. Now, the part I would put on a test is this next part, which is pretty easy. We got a table that we can use to come up with this series. We'll do these 2 problems and we'll take a break. It's not necessarily just trivial, though. You see. Yeah, because you see they still are looking for the pattern here, aren't they? So what I do on a test is I might actually ask you to write it out this way and don't worry about forming the pattern. So keep that in mind. Okay, yeah, e to the x squared minus or over 2. And they got this, the formula is poor here, but we'll work with it. What they should have here instead of x's, they should have like another variable, like p or u or something like that. It's obviously e to a power, isn't it? So e to the p power from this one is 1 plus p plus p squared over 2 factorial plus p to the third over 3 factorial all the way up to, let me put another one, 4 factorial plus dot 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 p to the n over n factorial. So what would p be equal to? X squared over 2. So then we're going to plug in x squared over 2 in for the p and try to see if we see a pattern. So 1 plus x squared over 2 plus x squared over 2 squared over 2 factorial plus x squared over 2 squared 3 factorial. I got something wrong. That should be the third power. There we go. And x to the x squared over 2 to the 4th power over 4 factorial. Dot, dot, dot. Okay.
How did you know it was x squared for the second?
It's whatever your power is.
Oh, it's whatever your power was. Okay.
Yeah, that's why they really should have something besides x, because if you have an x there, you're saying x is equal to x squared over 2. It's like, what? But it's like a u substitution type thing, except for it's easier. At least that part. Recognizing the pattern. And I could probably do some of this. 2 factorial, that's probably 1 factorial, that's probably 0 factorial, if I had to guess. 1 factorial plus 2 factorial plus 3 factorial. And this is third power, fourth power, second power, first power. So x squared over 2 to the first power, x squared over 2 to the 0 power, x squared over 2 to the third. I'm messing something up here. That should be a 2. X squared over 2 to the third power, x squared over 2 to the fourth power, 4 factorial, dot, dot, dot. This is n equals 0, or, boy, been off all day. I didn't get much sleep last night, but I feel better now. Calculus is healing me. Healing power of math. I've been teaching computer science all day, and I think that's destroyed some of my brain cells. No offense to whoever's going to computer engineering. Well, that's obviously n factorial on the bottom, right? This appears to be x squared over 2 to the n power. And that would match all of it, wouldn't it? They probably simplify that if I had to guess. Usually you don't leave a fraction inside of a fraction. So raise both top and bottom to the n power, so that'd be x to the 2n. Or 2 to the n power over n factorial. Leave the x to the 2n power on top, take the 2n down below, and we get 2n, 2 to the n power times n factorial. I'm going to check, see if I actually got it right. X to the 2n, 2 to the n factorial. Yeah. It'd be hard to get that one wrong. It's a pretty easy pattern. Take a look at one more of those. Is this making sense, more or less? There's probably one or two of you that can just see these patterns, and that's fantastic. I wish I could, but I never have been able to. Guess if I'd been working in the War Office during World War II, we wouldn't have won World War II, huh? It took us longer. Didn't they break the code that the Germans were using, so they could see all their transmissions? So, yeah, 1 plus x. Okay, so let's go look at our form. Again, I'm not going to put an x there. I'll put another variable like p or something. So our formula says natural log of p is equal to p minus 1 minus, this might have been one I didn't see a pattern on. I don't know. We'll see. P minus 1 squared over 2 plus p minus 1 to the third power over 3 minus, so signs alternating, p minus 1 and 4 over 4, and then so on. So based upon that, what would our p be? 1 plus x, so whatever's in there. Now let's plug that in. Oh, yeah, I remember this. The ones cancel out on each one of these. So this would be 1 plus x minus 1 minus 1 plus x minus 1 squared over 2 plus 1 plus x minus 1 to the third power over 3 minus 1 plus x minus 1 to the fourth power over 4. And all these is ones cancel, so I got x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. And that first one I could rewrite as x to the first power over 1, just to make the pattern complete. And keep in mind this keeps going. I'm not putting dot, 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 but it does. Assuming this is n is equal to 0, and then it's n equals 1, n equals 2, and n equals 3. Come back to the negative. This is 1, that's 2, that's 3, that's 4. They're 1 greater than n, aren't they? So this would be n plus 1. And this would be x to the n plus 1. And it starts out as positive, so this should just be n, I think. Because if you put 0 in, negative 1 to 0 is positive 1. If you put 1 in, negative 1 to the 1 is a negative, and then it alternates. And that'll be our answer. And that's a good place for a 5-minute break. We're done with that section.